All right, welcome everybody. 10 o'clock. We'll get going here. I'm Jim Hall, past president and owner of Systems Management and Balancing in Des Moines, Iowa. Had the good fortune of starting a semi-retirement, we'll say, a year ago. So enjoying that by doing things like this. So welcome. Here to talk test, adjust, and balance lessons learned for engineers, CxEnergy providers. If you've seen me do something like this in the past, very similar. Basically, let's see here, for the Atlanta Winter Conference, WABC asked if I'd write a paper based on this presentation. So I wrote a technical paper, or a transaction paper as ASHRAE calls it, that got published 2023, that'll have this information in it. If you get online, I think it's a whopping $6. Good luck finding it. I had trouble finding it myself. I was going to print off some copies. I can't find it, so I got one copy. So based on that, course description, the biggest thing about the course description that I'd want to say is the TAB process. Our goal in TAB is always to optimize system performance, improve design intent. That's probably one of the biggest things we are looking to try to do when we're out there developing a report, getting data, and that type of thing. So through that process, through 20 plus years of TAB work, I previously mechanical contractor, I sold equipment for quite a bit of time. You run into challenges on every project. So, and that's what really we're going to go through, a lot of the challenges we run through, how to address them, what we've come across, and that kind of thing. Learning objectives, understand the proper use, application, limitations of TAB instrumentation, provide an overview of HVAC systems and the TAB process. So a lot of that's just how we're setting up, how we obtain data, and that type of thing. Understand what's accurate, usable, meaningful data, so that we're getting data that applies to the project, applies to the owner's needs, the design professionals' needs, and that side. And a big thing that we always try to do is promote a project team approach, getting everybody involved that we need to get involved on the project. So as I mentioned, it's lessons learned. A lot of times, I'll say we're very fortunate and also at the same time unfortunate on TAB projects. We get out there, everyone's a learning experience is what we try to look at. I will say this thing we've learned, if a job is very clean and very good, and we go through and we're able to get all our data and things go great, technically we don't learn a lot. So it's the unfortunate projects that we learn a lot, and that's what you're going to hear a lot of this, of what we've run into on projects and that type of thing. We're very fortunate. We're the one company that comes in with the controls contractor and a project, and we're now putting all the components together. We're making the pump is connected to the chiller is connected to the coils, et cetera, and now we have a complete functional system. And that's where we get fortunate. We get to see, does this really work as intended? So we always like to start, and it was kind of nice. I sat through the 6 sessions yesterday with all the TAB work and that type of thing. And a lot of it was kind of interesting. Majority of those sessions all started off with the same thing here of document review and starting early. Get the TAB companies, get the commissioning agents involved early. And the earlier we can get involved in project document review, the better it is. As y'all can imagine, it's easier to fix things on paper than all of a sudden trying to fix a piece of equipment that's shipped on site that we're saying, oh gosh, it should have had this, or it shouldn't have been this, or whatever. Or looking at the ductwork saying, why is the ductwork running through here when it shouldn't be here? It should be over here. Catching these kind of things on the documents a lot earlier is very, very beneficial. We always like to call it and look at it as a document review. We're not looking at the load calcs and the design phase of that, everything, when we're starting to look at it from the TAB agency perspective. We're looking at system functionality, design intent, owner requirements, project building usage, and those type of things when we go through it. So as we go through more slides here and we go through this presentation, as we're discussing some of these items, think of how can I address that in the document review, and how can we make that system better, not only just for TAB purposes, but for the owner's purposes. The biggest thing we also look in that document review is really drawing coordination. Trying to make sure the drawing specs, the details, the individual drawings, the whole package are all coordinated through the project or through the drawing set. Simple things, sequence of operations states that the chiller is going to be communicating via backnet to the DDC system. Making sure that in the specification under the chiller, it says that they're going to provide backnet communication. The next caveat of that would be how much detail you need to get into on that backnet communication. What is the chiller manufacturer really going to provide that the DDC company can use? Is it a read-only point? Can they use that information? How are they going to use that information? So a lot of times it might be getting into the woods on some of it. Some of it might just be simple of project had about 50 exhaust fans with damper end switches. Specification said that the exhaust fan supplier is going to provide the damper and the end switch. In the sequence of operation was conflicting of who's wiring, connecting, and doing all this work with all these damper end switches. Well, there was no talk of the communication protocol required for the damper end switch, and all 50 of them didn't work. So things like that, little things you come into of, we get a lot into package controls now, manufacturers providing the control valves, things of that neighborhood, that making sure if the manufacturer's providing the control valve, he's got the right control valve signal and actuator that's going to communicate with the DDC manufacturer. So trying to get the coordination of those drawings, you know, what's shown on a detail is actually what they want. You know, going through pump details all the time, making sure they're tapped correctly. Too often in the field you get out and you see a pump is tapped and they're tapped into the air vents of the pump. They're not actually tapped into the test ports of the pump. So, and it's actually even shown that way on the drawing. So working on that drawing review, going through sequence of operations and that kind of things, and the earlier we can get on it, preferably during design, is very beneficial for the whole team. And when we look at that, we start looking to say what's required for tab data and what kind of tab data are we going to ask to get and what kind of tab data can be produced. Keep in mind, that data is a product of system design, equipment selection, system installation, system operation, and proper use of the tab instrumentation. So all those caveats come together and then allow the tab company to come in and get that data. So if design is different or layout is a challenge, looking at duct-mounted grills in the upper right, getting accurate airflow measurements, that's very difficult. Or you're out there looking at the installation. How is that installation shown? Control valve mounted right over the test ports of the balancing valve. How to use a flow hood, and better yet, even just making sure access to equipment's okay. Piping, electrical, all the utilities coming to it aren't blocking all the access doors and that kind of stuff. So all the different caveats of that can affect how the tab company can actually get their work done, or even the commissioning company can get their work done. We'll hit some of these items further as we go through it. As you look at it, you say, what data do I need, or what data is good for this project? Try to think what's meaningful data. You know, what is going to prove design intent or optimize system performance? What type of project is it? Is it a lab? Is it a school? Is it an office? Is it a strip mall? That's going to also dictate what data is needed. You know, do we need room pressurization for a spec office building? Building pressurization, yes. Office-to-office pressurization, probably not. So the hardest piece of when you're looking at those documents, saying what am I looking for, what do I need to make note of, is how will that data be obtained? I don't know how many people here have spent time in the field with a tab technician. Hopefully a decent amount. I can say if you never have, it's well worth the time to go spend a day or two with a tab technician. Pick some optimum times, look pump measurements, filing out an air handling unit, those kind of things. Seeing how they do it, what they do, what access do they need, and those type of things really can make an impression on how am I going to design, lay out a job, what am I going to do. So, but if you're that tab company and look at the drawings ahead of time, that's what you're going to be looking at when you're looking at those drawings, saying, Mr. Engineer, hey, we can't measure this airflow on this unit. This is why. Can we rearrange some things? Always keeping in mind it's field testing, it's not laboratory testing, so we don't want to get into a situation, well, they can get that data, but it's based in a laboratory setting. Okay, we're not a laboratory setting. So we'll get into a little bit of that later. But always keep in mind, a lot of times the tab company can get data and get information. It just might take more time and more effort. And it could even mean that we're going to drill a unit out and put a bunch of holes in that unit. Do we really want to do that to get a temperature traverse at the entering side and leaving side of the cooling coil? Do we want to do that to that piece of equipment? Is it really critical that we have that kind of data on that unit in that certain situation? If it is, yeah, let's get it done. Let's make sure everybody understands what needs to be done to do it and spend the owner's money wisely, because that's pretty much what we're doing. If we're going to do a bunch of things to get a bunch of data that's not needed for the project, why did we do it? Because the spec said to do it, but did the owner benefit or the design professional benefit from that data? You know, a couple examples we see quite a bit, wet bulb temperatures, entering and leaving a cooling coil. Just like I said, one thing, you have to do a temperature traverse across that coil. You can't do single point temperatures. Technology today is getting better that we can place sensors inside units now, Bluetooth back to a device and get a lot of good data that way. I'll say it's getting better. We've had several devices fall into the condensate drain pan, et cetera, et cetera. One went through a fan. So they're getting better, that they're not there yet. But in the meantime, we're going to drill holes to get a temperature traverse across that coil. Do we really need wet bulb temperatures entering and leaving that unit? Sometimes, yes. We have a process, so we got to verify that coil is going to do everything it can do. However, keeping in mind, can you establish a latent load on that coil? So that the data that you're getting, is it meaningful data? Or are you just getting data and you're getting that data, but you don't have a load on the coil? Or your chill water system isn't locked in and you're not providing 42-degree water consistently to it and getting a steady state condition. So we get into some situations, say, I want those BTUs off that coil, air side, I want it off water side. I want to compare the two and make sure they match or within 10%. How realistic is it to get that data and how much trouble we have to go through to get that data? Because you're going to have to establish a load, steady state conditions, and not be able to use what we'll call snapshot temperatures or getting a single point temperature to get the data. You can get some single point data, and some of that stuff can work out pretty well to get you an idea of what's going on. But be careful when you start asking for these things of these wet bulb temperatures and know what you're really getting. And if you're going to start trying to plot those out and say, my coil's not doing the capacity it should be doing, we need to step back and look and say, how much data do we get? What do we have? Remember, not a lab condition, it's a field condition. You know, a lot of times we'll also see dry bulb temperatures entering and leaving a condenser, air-cooled condenser. Outdoor air temperatures is going to affect that, as well as what the compressor load is. Do we really need to get those numbers? If you're looking to say, how's my unit doing? A lot of times it's going to be go back to and look at that startup report from the company that started up that system. See what the refrigerant pressures are and everything in that side. Keeping in mind, I don't know, how many tab companies that are in here carry refrigerant gauges? 0 hands. We don't, never have. Predicated really, I think, all from the start of the fact if we penetrated that refrigeration system, we just voided the warranty. So that started the battle of refrigeration. The other side is refrigeration is a whole nother subset, a lot of education required. So we don't focus on refrigeration. So don't get caught up with your tab company typically not doing any refrigeration work in that side. There are some I know that do. One of the big things, like I said, when you get out in the field, if you have the opportunity to work with a tab company or a tab tech, is system operating mode. And that's one thing you're thinking when you're going to get data, what mode of operation is this air handler in? Is it minimum outdoor air economizer mode, 100% return? Is there diversity in the system, pumping or air handling wise? How am I going to set that system up? What's my connected load at time of test? You know, and sometimes we might be tasked as a tab company to come in and say, I need to test this unit, or maybe we'll say this exhaust fan in normal operating mode, but then I go into emergency purge mode. I need to know what it does in emergency purge mode. So we might have to test in a couple different scenarios. But one thing a tab company needs to do is do a good job of, one, is telling you how they tested it in their report to support the data that they've got. So you know, a lot of times we go out there and we get numbers to match up and match up design numbers, but we also want to look and say, how did we set that system up to do that? So if we got design numbers, were we operating in the right mode? Because a lot of times we'll go back out and say things aren't working right. We didn't have it in the correct mode to test for that scenario. So think of that. Majority of the time, your tab reports can be tested in a maximum operating condition. So we're going to see what that fan can do, fully connected, load connected, or actually a lot of times, if it's diversity on an air handler, we'll open it up and have 30,000 CFM connected to 25, see what the unit can do, make sure the fan doesn't overload, et cetera, et cetera. So there are certain situations what we'd look at, but most of the time we're looking at a max operating condition, making the assumption from that point operationally that if we can produce up here, once the system goes under control, the unit's going to be able to produce load under here. So if anybody has any questions at any time, holler. We'll answer them at that time, hopefully to address, use slides or whatever. So minimum flow. So minimum flow, a lot of times what you'll have to do and what we'll do is we'll back the unit down to minimum flow. So let's say we have VAVs connected up to the system. We'll drive all those, index those to a minimum airflow set point, see what the air handler does, make sure the air handler runs stable. Today, majority of your fans, I don't see falling off a fan curve. We've had it in the past. We get down to minimum, it falls off the curve and it starts rocking. So, but you'll run a test, drive your boxes to minimum, set the system up that way, or even on your pumping system. You might drive your system back down, back off so many control valves. So you want to usually go min-max cases. Thank you, Galen. Tolerance is another thing to think about when you're looking at data. And you're looking at that spec. If they're looking at 0% to plus 10, minus 5 to plus 5, stop, call a timeout, and see why they want to do that. We can go balance a system at 0 to plus 10 and try to set everything at that set point and get everything there and measured there. But if that control system is turned loose at that point, most likely it's not controlling 0 to 10. It's controlling probably minus 10 to plus 10 or some range in that side. So you go back to prove up, now all of a sudden your numbers are below design number, they're below the 0%, so hey, you need to rebalance it. Well, how's the control system controlling? You know, better yet, plus or minus 5. We'll balance the plus or minus 5 tolerance, but is the control system can control to that level? So are we doing something that's needed in that situation, in that scenario? So sometimes, yes, it is. And if it is, most likely your control system might be fine-tuned or something there to compensate for it, but make sure everybody understands what they're looking for when they ask for those tolerances. The other piece of it is you can even look mechanically. Rooftops are always my favorite equipment. Outdoor air on a rooftop. One, trying to measure it, whole nother caveat, we'll talk about that in a little bit. But two, a lot of times they're gear driven, multiple gears, and you can go out there and grab that outdoor air damper and move it ½ inch, if not more. Same thing with even the damper actuator in the shaft. So you set a minimum position for that outdoor air damper, and you've got that set up and you're going, but yet the next time it opens all the way in economizer or something comes back, it's very seldom coming back to that same position because of the slop and the damper play or the gear play. The other thing on rooftops, keep in mind too, live in Iowa, we always get a lovely northern wind all the time. Don't face your outdoor air openings to the north wind. At that point, then you can probably have an outdoor air damper closed and still get 10 or 20% of outdoor air, typically in the wintertime in Des Moines, Iowa. Actually, right now in the springtime, we've been, a calm day for us has been 20 mile an hour, so it's been great. Not if you like golf. So you got to think also of how's that equipment controlling, thinking that in your tolerances. A lot of people say, I have a lab or an OR. I've got an environment, I need tight tolerances. Think about it a lot of times in lab and ORs, air changes per hour is going to dictate your air volume as well as your room pressure. So if you have a tight room, you're going to have to start making some adjustments to your exhaust, your outdoor, or your supply air to maintain that pressure. And now all of a sudden one of those is probably going to be more than 10% out, or if your room is too loose. So that can dictate you not being in tolerance of airflow. So don't get hung up that I've got a critical environment that really needs to be controlled very well, that I need to balance this to plus or minus 5%. A lot of times your airflows aren't going to be in that range because we're trying to maintain a room pressure and air changes. So, one last thing, we'll go through design equipment selection. Once again, that could affect your tab tolerances and what can be obtained. We'll talk like some balancing dampers, that kind of thing in a minute. Another little quick caveat, your instrument manufacturers across the tab, they're all very similar. We'll go airflow, velocity, or air volume, CFM, feet per minute, plus or minus 7 feet per minute, or CFM, plus or minus 3%. So at 100 CFM, you're plus or minus 100, or you're plus or minus 10%. You get to 200 CFM, you're plus or minus 6.5%. So airflow goes up on those devices, accuracy gets better. Airflow goes down, accuracy gets worse. So it's kind of funny, a lot of times we look to get tight tolerances on 35 and 50 CFM because that's our outdoor air coming into the space, and we got a dedicated outdoor air system. Down at that level, you're 13, 14, 15% plus or minus in accuracy of the instrumentation. So keep that in mind also when you're looking at that in those scenarios. Below 100 CFM, 100 feet per minute, you're going to get above plus or minus 10%. Layout accessibility, one thing when you're looking at those drawings, you're going through that review, not only do we need access to equipment, we need access to the balancing dampers, the balancing valves, the test ports, the inlets and outlets, the ductwork for traverses. So we need all that kind of access into a space, not just to the equipment. And also looking at, when you start looking at sheetrock ceilings and different types of architectural features, you know, if we got, hey, we got an access door, like in this case here, access door is there. I took the picture from the access door. It's sad that the cooling and heating coil and the balancing valves are on the other side of the unit. Filters at the back end of the unit, the balancing dampers way down there at the duct tap, you can't get to anything. So access doors in, hey, we're good. You know, we're accessible, other than the fact you can't get to anything. So things like that you got to look at and say, what all do I need to get access to and that type of thing. It looked great when the sheetrock ceiling wasn't installed. And everything's there. Hey, if we can get the unit started up and it could be operational at that time, we could probably go through and set everything. Nothing was operational at that time. So you get some challenges like that you got to typically look at and think about on that side. So a couple caveats on that. Different scenarios, sheetrock ceilings, architectural features, you know, acoustical one, but two, we got to hide this ugly HVAC equipment. We got to cover it up, you know. So that's what they do, and we get those lovely architectural clouds in. You know, I laugh in the one picture there with that outlet, ductwork's going to a balancing damper up there somewhere. I don't know how we're getting to that balancing damper. So while it all looks good, and we got a cloud, and we got this, and on that job site, those panels weighed over 200 pounds each. We weren't moving them, let alone the expense of them. So if you damage one, you don't want to be there either. So things like that, those architectural clouds and that type. Theater seating, always a big one. Auditoriums, that type of thing. You got your ductwork, grills up high, possibly architectural features covering it. Seats are not in when all this is getting installed, right? Scaffolding's built, lifts are there, everything's going great. Okay, we're starting to put all the seating in, we're getting all that stuff, equipment's still not running. So we can't even get in there to get through and look at the ductwork, get to the grills, do a duct traverse, get to the balancing damper. So what kind of access is there going to be for that? A lot of times you'll have a VAV box up in those auditoriums, hidden by a cloud. How's the owner going to get to it later if the actuator fails? Hot water coils, strainers. So a lot of those kind of things in auditoriums, natatoriums, ductwork going over the pool. If we have that ductwork on the perimeter, a lot of times it's better. Things like that you got to look at when you look at those drawings. Hey, we can save a lot of scenarios, and create a lot of opportunities to get airflow measurement, water flow measurements if we look at these things before it happens. Lately, we run a ton of flex space, 20-foot high ceilings. They're going to rent it out to whoever wants to rent it out. Guy came in, put his 12-foot drop ceiling in. Owner of the building said, hey, I want all this ductwork up tight to the structure so that if we lease out to somebody in the future, change the space, I don't have to move my ductwork, et cetera, et cetera. Go in there, pop a ceiling tile, get to a balancing damper, 12 foot high. Oh, I got another 8 to 10 feet to get to the duct. There's no way to get to the duct. There's no way to get to the dampers. So the old adage at the standpoint is, well, you should have done it all before we got the ceiling in. The outlets weren't installed until the grid was in. And so you run into some coordination issues in that scenario that everybody starts thinking, oh, wow, we didn't think about that. So things like that, when you look at those drawings, you know, sometimes we got to look outside the scope of our mechanical drawings and look at the architectural drawings and see what we have. Like I mentioned earlier, equipment selection, a lot of times you get everybody together and you're starting to look at that, get the suppliers involved early before they order the equipment. You know, kind of a messy drawing here of a unit, evaporative cooling unit. Believe it or not, the evaporative pad, the green pad, is parallel to airflow. The airflow is coming down on the bottom side, makes a 90, goes up and through. They wanted us to measure that pressure drop across that media, confirm the installed magnet helic to that. There was no way for us to get in there and get that pressure drop across that filter media. We went door to door with all our pressures and correlated what pressures to what. So in the long run, they had a chart on the side, design this, their magnet helic was this. We measured this as our pressure drop across the media, but that pressure drop across the media was actually between two of the access doors, not directly across the media. So if you're going to need some numbers like that and some proof, or better yet, they want to calibrate and make sure their sensors are right, we need to make sure with that supplier that we have availability to test ports, or they're going to run two off to the doors to match up. And that's all they really had to do is tee off the tubing they had, put a set of test ports on the exterior of the panel, and they said that wouldn't have been that bad to do. We know that ahead of time, we can get those kind of things taken care of in that scenario. You know, keeping in mind also, thickness of that unit can also play a big role. If it's 2-inch or 4-inch panel, drilling through that whole panel to field drill, to get it sleeved and that type of thing, better if the manufacturer does that at the manufacturing plant and that type of thing. Same thing on outdoor equipment. Test ports, we shy away from drilling external units just based on outdoor equipment. One, because penetrating that casing that's going to be sitting outdoors, then plugging that hole back up. The second reason why, we've drilled into too many components. They pack a lot in an external outdoor rooftop unit. Energy recovery units, you know, you've got everything in the world in there between your heat exchanger, DX, if they got hot water, chill water. There is a lot going on in that between your exhaust and return path, or exhaust path, supply paths. So if that's needed, let's spot some places where we want to get pressure drops, get the factory install the ports up front to allow us to get pressure drops, temperature measurements of where they want them. It's kind of interesting, a lot of times now on a lot of the units, especially energy recovery, they do give you test ports across their heat exchanger because they want to know what that pressure drop is during operation. So some people are starting to catch on to that and that type of thing, but you get field equipment, outdoor equipment, really take a look at it and say, what do we need for information? What do we want the tab agency to get? What's the manufacturer going to need during startup and that kind of thing, so to make sure all that gets taken care of. Airflow measurement. I'd say one of the biggest things you could take away from today, if anything, when we measure airflow, we want a duct traverse. That's the primary preferred airflow measurement method, and that is the most accurate method that we have available. ASHRAE 2021 Handbook of Fundamentals, they define a good traverse plane as 7.5 equivalent diameters downstream, 3 equivalent diameters upstream. Formula to get your equivalent diameters for rectangular duct, round duct, it's just the internal diameter. We also like to see better than 1,000 feet per minute for a velocity to get a good accurate duct traverse. Give you an idea.
Jim,
Yes?
there's no longer a requirement like that for traverses.
For,
As long as you have a straight duct, you have 1,000 feet per minute, and you don't have any negative or zero readings in your traverse.
we'll get there next slide.
Okay.
So the Ductwork, 30 by 12 ductwork, 10,000 CFM, 2,400 feet per minute. If you're looking at that straight duct, you're going to say, I need to get that equivalent length, you're looking at 24 feet. So 17 feet upstream, downstream, 7 feet upstream. So, and I know we get that all the time. Mechanical rooms are so spacious, they're built, and they're concerned about our duct runs and that type of thing. So that's, and Galen brought that up, we'll go through that in a sec. One of the reasons why is we don't have this ductwork all the time. So one of the things that I kind of laugh, dated article to a point, ASHRAE Journal article, February 2006. Canadian School District did a study across there, I think it was 20 to 30 schools. Started looking at all their mechanical rooms, started looking at their duct runs, started looking at system effect, and started looking at and running calculations. Their base calculation was a difference in 6.7 brake horsepower equal to about $1,200 per year in increased operating costs due to the system effect that they're seeing. So they started running the numbers on that and said, okay, over a 25-year period, I think it was 6 cents a kW and a 5% increase, escalation in energy costs, equated to that 25-year life of that building at $86,000 on just 6.7 brake horsepower. 30 schools, multiple fans, you can imagine what that number starts adding to. So we look back and say, to avoid system effect, typically, you need a good straight duct run. So you need a good place for a traverse. So a good caveat, if you're looking at a situation, you got some conglomerated ductwork, is making sure those people understand the energy cost impact they're going to have on their building by cramming all this into a mechanical room to get more square footage. The best part of that article was there how to avoid this increased operating cost by not trying to save dollars per square foot by reducing the size of the mechanical room. The increased operating cost of the poor installation is likely to be far greater than the cost of providing the space necessary to ensure a good ductwork installation. I still use that all the time when I'm visiting with architects or engineers. Say, hey, by the way, great article. Take a look at. The other side is performance. How much you hurting your performance of that unit, and all of a sudden we can't make airflow, and the unit can't perform because of that ductwork situation. So, and just as Galen had mentioned, a ductwork can still be performed if an ideal traverse plane is not available. So if we don't have that spot, we're still going to take one. And we're going to look and see what that velocity profile looks like. So if 75% of the velocity measurements are greater than 10% of the velocity of the maximum velocity measurement, and none are zero, it should be, say, zero or not negative, you've probably got a good velocity profile. Now, with that good velocity profile, we can look and say, we've got that airflow. Another thing we can look and then say, how much do we trust that duct traverse? We can look at some other options and start saying, face velocity coils, heating coils, cooling coils, pressure drop across the coils, face velocity of air filters, summation of airflow of your outlets, summation of your VAV boxes. We start getting a little more, and I always hate to use the word art than science, or the phrase art than science, but we start then looking and saying, what can we compare to that traverse with other data to make sure this does make sense? RPM of the fan, amp draw. We start looking at those things and start saying, okay, hey, we're going to prove this number up a couple different ways. So there are some methods we can look at and try to look if we don't have a duct traverse, but I can tell you what, you can save a lot of headache in the long run, a lot of projects when you start having problems if you can get a duct traverse. One thing also, we start running a ton of fabric duct now, a lot of fabric duct. Two things to think about when you're using fabric duct. One, if you have that fabric duct branched off and you got a bunch of branches, make sure there's a means for balancing dampers. A lot of fabric duct manufacturers do have devices. Basically, it's a concentric device that'll close down at the inlet of that fabric duct, reducing airflow, or a balancing damper. Second thing, duct traverse. There's no way to measure that airflow going into that sock if we don't have a place to do a duct traverse. So if you want to know how much airflow is going down that duct sock, typically what we'll see is, say there's 4 branches of duct sock serving in here. We got a main coming in. We'll traverse that main. Usually we've got a good duct to do that. And then the branches, we usually can't measure the airflow. we might try to take some static pressures and correlate back to some static pressures. A lot of times, unfortunately, it's a visual indication. My duct sock's not overblown, and my duct sock's not sagging, it's not noisy, we're good, we know we got total airflow to the space, the duct sock looks good. But if we extend that metal duct a little bit, enough to get us a duct traverse, can make a big difference in that side. So if you see fabric duct, think of how's the airflow measurement going to be taken. Second biggest thing I can say about airflow measurement, we'll take away today, is the flow hood. It's not an airflow quantity measuring device. It's a proportioning device. So when you look at that and say, how am I going to use it? I get pushback on the far left one with the flow hood. There are some flow hood, or fume hood. There's some fume hood manufacturers that say this is how you're going to set up my fume hood. But if you think about it, you're taking a 4 foot wide by 2 foot high opening and reducing it to a 14 by 14 inch opening. Is that going to really be a true airflow measurement of that fume hood opening when it's 18 inch by 4 feet? So, not a fan of doing that, especially if it's a single fan doing it. You've just overloaded that fan probably because you've made it more difficult to get the airflow, you back pressured the system. VAV systems, you typically get away with it with an air valve or whatever, because what's that air valve do or the VAV do when you do that to that hood? It's set for a set point of airflow to maintain a velocity, right? It opens up. So it's probably set 100% open in this situation. So know how to use the flow hood and its limitations. Middle one, we love 2x2 plaque diffusers. They read very well with the flow hood. The one on the right, putting it over a duct-mounted grill, we can show you how we did that and what we would do and how that would make sense in the long run. But getting an airflow measurement and saying that airflow is exactly that airflow coming out of that grill is not correct. So all your flow hood manufacturers will say they require the development and use of a K factor when used on swirl diffusers, other type of diffusers with uneven airflow, and also high velocity jet diffusers. So nozzle diffusers, laminar flow diffusers, security grills, anything where that airflow is a jet coming through, that hood is not going to read accurately. So you can look and say on the left there, I apologize. The bottom of that hood, you see a flow cross of black in there. That's that velocity grid. If you look on the bottom of the hood that's hooked up the fume hood, that's your velocity grid. That's what's measuring a pressure coming across that grid. If it's uneven across that grid, you're not going to have a good airflow. So one quick little instance, we did a project that had multiple heat pumps serving 6 or 8 eyeball Ponca diffusers. So to go through this thing, we looked at it and said, how do we want to do this? Because there were areas where we could not get to ductwork. This one, we can get to the ductwork. We traversed the ductwork, traversed 113 CFM to 1 Ponca diffuser. At that point, we took 2 techs just to make sure, had them measure it 5 different ways, 3 different measurements in each way. Pitot tube, airfoil, rotating vane on the opening, everything at the opening of that eyeball. We use the flow hood 2 ways. One, we call it a blast plate. Luckily, the manufacturer now is making some things of this neighborhood, but that piece of cardboard in there. If you imagine that reason that was put in there, that jet airflow hits it, disperses it, we have a more even airflow going across the flow grid now. So, and we did it without the blast plate. When it all came said and done, we developed a K factor for each device and which one we felt the most comfortable with. So you can look and say, the flow hood without the blast plate, not right. We had airflow readings all over the board. Don't do that. If you do it, put the blast plate in, it's got to be in here, it's this size, et cetera, et cetera. Whatever reading that says, we're going to take times a 0.84. So it was reading a high airflow based on the duct traverse, so we measured 113. Or we can go with the rotating vane and say, okay, we're going to take that measurement times 1.078. Everything went back to the duct traverse. So there's ways to get around getting airflow measurements. We were lucky we had a couple test cases we can work with. So when we got into the areas where we couldn't get to ductwork, we had a method then set in place of how to do that. So, but you can't just put that flow hood up there and do some things. And a lot of times you just can't take a face velocity reading and get a reading. So you're going to have to look at that duct traverse to try to get you a good gauge of what's going on. Outdoor airflow, looking at the drawings. Once again, our mechanical rooms are like the size of this room. We got great space between the outdoor air louver and the unit. I don't think I've ever seen it in my life, and I've only been in the industry 35 plus years. That outdoor air duct comes right out of the louver and goes right to the unit, right? We slope it up and dump it in the top. The outdoor air louver comes in. We've got, in the picture on the right, we got a min outdoor and we've got an economizer outdoor connecting to the louver right back behind the unit. How are you going to measure that airflow? You know, and outdoor airflow becomes pretty pertinent these days in a lot of what we're doing on job sites and that type of thing. So if the outdoor air is going to be critical, give us a way to measure it. You know, we need duct traverses preferred. So you have to get very creative in scenarios of putting the system into 100% outdoor air and doing some different things and try to set some things up of what can I do for measurements and then try to get damper positions that might correlate. Variable air volume system becomes very difficult because then your fan speed's changing too. So you can get into some very difficult situations to try to prove up outdoor air, but if we're looking at those drawings ahead of time and tell everybody, hey, here's your problem, what can we do? Then we can try to address it up front. Like I mentioned, rooftop units, you can't put the hood on the back of it. They become difficult to work with. Mixed air temperature method, I don't know how that's going to work here in Texas and Iowa. Yeah, in the wintertime, we got very cold air, so we can use a mixed air temperature method. 30 to 40 degrees difference between your return air, and outdoor air, and then making sure you got a good place to measure your temperatures, especially your mixed air temperature. Sometimes we'll look and say, if I can get a duct traverse of that supply on that rooftop, a duct traverse of the return air on the rooftop, supply minus return, that'll give me a good ballpark of it. Keeping in mind, your measurement tolerances could be plus or minus 10%, plus or minus 8%. Guess what? If you have 10% outdoor air, you know, you're looking at a situation saying how accurate is that supply minus return. However, a lot of times what we've done is a lot of rooftop units, we keep a spreadsheet and start looking and saying on certain manufacturers, if that damper's at this position. And a lot of times when we say position, we'll also measure that blade gap opening to know a half-inch blade gap opening, you know what, that's going to get us roughly 10%. You know, and a lot of times you can look at the damper manufacturer's performance curves and you get them from them and look at that and say, all right, that's going to get me in the ballpark. And that might be your only means or method for a rooftop. Unit vents, we see a lot in our schools getting remodeled. They're putting a lot of unit vents in. And, you know, you get a schedule, 35 for minimum outdoor CFM, 130 for max. There's no way to accurately measure those. And getting people to understand that, and they went to the whole trouble of specifying this, saying, here's what I need. Unit vents, if that unit's installed in the same configuration, no added ductwork, the louver that they put on there in the factory and sold with it is the louver that's used on it. You can use their manufacturer published data, and you're going to have to use that to set the positions to the damper. They know it can't be measured in the field. They do have charts set up to give you what those airflows are at the damper opening. So one thing, just make sure the architect did not get his hands on that louver. We had a situation, and it created a nightmare. Not only for the outdoor air, but they were DX. They were all tripping out on high head. They forgot to put the baffles in between the condenser air and the intake air. So they couldn't figure out what was going on in these things. So all of a sudden, somebody looked at the, well, I said, who provided the louvers? Well, the architect. Oh, yeah, those are special. And they pulled one off and said, no, that's why. So be careful if that louver selection gets changed from what the manufacturer did. Don't get caught into the lovely thing of airflow monitoring stations. Hey, you know what? We can't measure there. We'll just stuff an airflow monitoring station in that duct. We'll be fine then. They need to be calibrated. They need maintenance. They need filtered air. And they need a good place to be put it with a good velocity profile. So when you look at where am I going to put that airflow station, a great place to locate that airflow station is where you do a duct traverse. You need a good even velocity profile. You need to make sure you maintain that for that airflow station. Now, keeping that in mind, if you have one on the supply duct of a air handling unit VAV, and it's all sized for max airflow, when that VAV air handler goes down to min, do you still have a good stable velocity profile that's going to work? Will that airflow station work across that range? That's why a lot of times you do see now the min outdoor air and an economizer outdoor air, and on the min outdoor air, they got an airflow station. Because if it were just put on one, when that damper closes down, one, it creates turbulence that airflow station doesn't like, and two, you start dropping below velocities that airflow station can't handle if it was sized for that whole outdoor air intake. So Ross Montgomery, I don't know if Ross is in here today. I talked to him yesterday. He wrote an article for ASHRAE Journal. It was the featured technical article in April, Filtering Ventilation Air for Sustainable Airflow Measurement. He goes through a lot of that. If you want to know to make sure you're applying an airflow station correctly, great article to go through.
I've seen a lot of manufacturing of rooftop units over the airflow station intake of the outside air.
Left picture?
Oh,
Yeah.
and I don't think those work.
Hospital, 6 rooftops. Iowa, all faced north. It was wonderful on that side of it. Their building was bouncing all over the place. The day I went there, hospital was incredibly negative. All the outdoor air dampers were closed, and I looked at the very first one. Thank goodness it was pouring down rain. They're all full of water. Yeah. So one, not filtered, not protected, and in a bad velocity profile, and exposed to the wind. So once the wind starts blowing on them, you have a big problem. So yeah. So it's funny. Airflow monitor stations are fantastic, but we just need to make sure they get applied correctly. Like we talked about, equipment, that can affect the balancing that gets done. Simple little thing of balancing dampers. Lower right, typically what we see the most. Handles are always buried in externally wrapped insulation. Can't find them. Set screws don't stay set. Believe it or not, you can close that damper on a 200 CFM outlet. Oh, my guess would be less than an inch of static pressure on it. It's still going to leak through probably 50 to 75 CFM. The upper two, external handles, extended handles, externally wrapped duct, we can mark them, they set well. They close off better, but keep in mind a balancing damper very seldom will close off to 0 CFM. But they close off better. You've got gaskets on all your shafts, so you have less leakage, that type of thing. The quality of the balancing damper can affect the quality of the portion that you're able to get out of that job. So, if you've got something where those outlet airflows really have to be tight and really have to make a difference, some lab airflows and some things like that might be a difference. You're serving a common space and that type of thing, you can get away with probably something on the lower right. That all that airflow and it's all serving a common space, you're not as particular or not as required to have that tight of tolerance of airflow. The other thing is locating it. Locating them close to the outlet. One, you have a noise issue possibly. The second piece you have is when you close that damper and it's closer to the outlet and farther from the main, you've added static to the system. You reduced airflow to that. You really didn't push airflow to the other outlets. So on that lower left drawing, they showed it going down by that outlet to the lower right. If that damper were located closer up to the 2 other outlets, the last 2 tapped off, going that duct out there, you have a better chance of pushing that airflow and keeping it up into that main duct. Keeping in mind, most likely the easiest outlet to get airflow to could be that farthest one. That straight duct run coming down, high velocity comes through. If the 2 outlets close to the rooftop are too close, you can actually get to a point where you're sucking air in. So the velocity is going across so fast, if it's a large enough system, high enough volume, you'll get entrainment on those first 2 supply air duct outs, inlets that should be outlets. So, but getting those dampers close to the main makes a big difference of being able to proportion that airflow and push it too. So location of the balancing dampers, very crucial. Balancing dampers, or I should say, in grills, face-mounted grills like we talked about before, there's really no good means or method to get that airflow measurement. Taking a face velocity across it, you can change that face velocity by changing your deflection vanes. You can set them up as the manufacturer's published data has, take your velocity measurements and use their K-factors they developed, and get a good idea, a good ballpark of the airflow. The second you start changing those deflection vanes, all gloves are off because you've changed that velocity profile and you have different jet effects. So The second piece of those is the face dampers. If I could do one thing in my life, I'd eliminate all face dampers out of our industry. They don't work very well. They'll reduce the airflow at that outlet, but you do not push airflow down the line. You do not get that done. They're noisy. They get dirty. Owners have access, so they want to change them. They'll change your deflection vanes all the time. They'll open those up, close them down. They're just not an effective means of balancing. If you have a run like this one here, damper upstream of the whole main run serving the common space, set your run for a total. Then you can use your face dampers to trim out, make sure you don't have any airflow issues with velocities down in the space, any jet velocities going on, that kind of thing. So you can do some things that way and do some things in that fashion. Trimming out works great, but to try to get it to a tolerance of a plus or minus 10% balance with a face damper probably won't happen. Little thing on drawing nomenclature. I always laugh, if you got a job with 100 VAVs or 100 heat pumps, and you open up the schedule page and you see there's 5 heat pumps listed or 5 VAVs, call a timeout. Get an individual identification of each one is crucial. VAVs has not gotten so bad anymore because we don't get to use the rule of thumb for minimum airflow anymore, right? Oh, 30%, just set those all for 30% min airflow. Now we've got to get a minimum calculated each space, or supposed to have a minimum calculated for your space. So you do have a good schedule on every individual VAV. But being able to identify them, on the chart, in the schedule on the left, VAV 11-1, anything with 11 was served by our handler 11. Anything by 12 was served by our handler 12. Things like that help make sense. So not just for the balancer or the controls guy or the construction team, but for the owner. When he's sitting there going back through and using it and looking at his drawings, one, what's in the balancing report, that tag matches the control drawing or matches their software, matches their O&M. Now they all have that. We all didn't decide to name it something a little different when we're out there. So heat pumps the same way. Iowa became a big heat pump. I call it the heat pump capital of the world at one point. It's backed off some, but variable refrigerant fan coils, same thing. You'll see an FCUA. Hey, how about an FCU A-10, room 10, A-12 for room 12. So you got all your sizes the same. You see your A, it's a size A, put a room number behind it or something. So it makes a huge difference, especially when the owner takes occupancy and he's trying to figure out what he has. Makes a big, big difference. Then work with the controls team and say, what are you guys labeling yours? We're going by the schedule. Perfect, so are we. One thing we're also running into quite a bit, pre-engineering, pre-demolition, pre-construction measurements. We hear all three terminologies thrown out there. A lot happened thanks to COVID, renovations, remodels, that type of thing, and trying to figure out what we're doing with those readings. So if you're seeing that you want to get those type of readings and see somebody defining those early in the process, the biggest thing I look and say is, why do we need the readings? What are they going to use? What are they going to be used for? We just try to look and say, okay, if it's pre-engineering, we're going to take them before design, and we're going to get those to help the engineer figure out sizing of equipment selection, that type of thing, performance and that type of thing. If we're looking pre-demolition, design's complete, but what we want to do is go out, take a measurement of that unit. It's going to get yanked out. They're going to put a new unit in, and we want to see if that's doing the same thing or better than what we yanked out. The one caveat I'll say is anything changed downstream of that pump or that air handler, just all gloves are off now. The readings you took before, the system's changed. You no longer can really use those numbers because the system changed. So be careful on pre-demolition. Pre-construction, we had a contractor that this is what I need, and I said, what do you mean by pre-construction? Their terminology at that point went to, we're not changing anything in the HVAC system, but we're adding a wing to the ORs. We're adding a whole nother set of 6 ORs, and when we add that wing, that corridor is going to connect, and that corridor is now going to communicate with the other corridor. We want you to measure all our pressures here, all our airflows here, the existing. We know we're making it now. When we add this after you balance it, we need you to go back and make sure we're okay there and that the system didn't affect that. So sometimes also engineer wants to cover himself and say, hey, it was working before, here are the measurements, it's not working now, what happened? So that kind of scenario. So the one thing to think about in those measurements, can they be obtained? I'm getting old enough that most pneumatic systems are going away or are being replaced. But if you have a pneumatic system, you really can't index a load. So if you got a VAV air handler, you're going to replace, say, well, I want all my boxes opened up. It's not a DDC system where you go and say, send all my boxes to max CFM, let's see what kind of airflow I can traverse. You can do what we did, pull control air, and they fell open, right? Great, we're 100% open. Put control air back. We just did the owner a great service on about a 200 VAV job that he now had roughly 100 VAVs that never came back, and he had to replace 100 controllers. We showed him where the failed controllers were, but he wasn't overjoyed at the situation having to replace them all now. So don't pull the main control air anymore. But you got to think, several times we're going to do exhaust fans. A lot of times we'll measure the exhaust fans, say, we need to know all the exhaust airflows through this school. We're going to replace them all. Or we're going to do this remodel. I can't tell you how many times we start doing that, and I bet you 50% of the exhaust fans no longer have electrical wiring to them. Belts aren't hooked up, et cetera, et cetera, et cetera. So, and it's always fun. No, we took the electrical off that. We don't use that fan anymore. So that probably should have gone to pre-engineering readings so the design professional knew, okay, they're not even using that exhaust fan, or there's no ductwork connected to it anymore. So sometimes if we're looking at those readings, how are we going to get them, why are we going to get them, and how's it going to work? Schedule challenges, probably the biggest thing is get the durations early, build it into the schedule. For the tab work to commence, clean filters are installed, strainers are clean, startup strainers are removed, balancing dampers 100% open, balancing valves 100% open, temperature controls clean and functional, and the last bullet item to make all the equipment started up and operational. So when we look at that, the biggest challenges really come in large projects, phased projects, areas, keeping in mind tab work's performed by system, not by area. So if this air handler serves floors 1, 2, and 3, we're going to finish floor 1, occupy it, then we're going to go finish floor 2 and occupy it, et cetera, et cetera. What are we going to do to be able to have that system operate to serve floor 1? Isolating it from floor 2. So those different things, when we get into phased jobs, area type projects, if that HVAC system doesn't match up to how they want to move in and how they want to utilize the facility, call a timeout. The one thing we've learned is in those type of situations, air-wise, a lot of times you can put some VAVs in, put a VAV in to serve that area, or a couple of VAVs to serve that area, calibrate the VAVs, balance all your outlets downstream. As long as you maintain static for that system, for those VAVs, you get to the second floor, you just have to come back and make sure the static's there. You don't have to go back to first floor. So you can use some VAVs in a creative way, exhaust systems, air systems, water. You're really probably looking at putting branch balancing valves in possibly, maybe automatic flow limiting devices, but at least some sorts of methods to measure airflow going to those areas that are finished to try to figure out what you have and then what are you going to have after the next area is finished. So scheduled jobs can become messy. You're probably going to have to look at it. You might spend more time figuring out what do we need to do to accommodate the schedule. Tab reports, quick and simple as I'm running out of time. Biggest thing is there's no benefit to a tab agency reporting problems or reporting issues. When I get a report in from a tech and everything looks great, and I'm going through, man, this is awesome, that's when I start getting nervous. I'm like, oh, really? There were no problems, okay? I started looking at it, I started asking more questions, and usually everything's pretty good. The problem with all the reports, which are 90+% of them, those are the ones you got to pay attention to, really, and look at and work with the tab company. Call them in. Hey, buy me lunch and let's go through this report. Let's look at this and see why you couldn't get design airflow. So that's why I make that comment. Because of that pristine report, did we just match numbers to match numbers? Did I have the system operating in the right mode to get that number? You know, there's different ways to be creative in that field. Just make sure they were creative the correct way. So, any questions? Ran a little longer than I thought I wanted to, but Right. That's our everyday life. It's a lot, you just have to work with them. So once again, if we're brought in early on the project and we can try to identify these things and go through it. Yesterday there was a seminar on scheduling basically. And it's really, if you could get your people to schedule backwards, when's the owner moving in? Okay, I need this much time for balancing the controls guy. Now what do I need next for those guys? I need electrical, I need startup, I need this complete. And work backwards on the schedule to get to your start date. That helps a ton of saying, what do I need? Here's what I need. And then when you get into phased ones, it really gets difficult and that kind of thing. But yeah, we run into that weekly. Yeah. You know, the only thing I'll say is, since commissioning has become more prevalent and more utilized, the scheduling has gotten better. Yeah. Good. Thank you all. Appreciate it.